How about the dynamics of a rigid body? You recall, when we considered the dynamics of a particle, we started with second law of Newton that said that for a point particle, force equals the mass times r double dot, or mass, the second derivative, the acceleration of r with respect to time. Later, when we learnt about momentum, we said force is nothing but dp dt, that is the rate of change of the momentum of the particle. The equivalent role that is played in describing the orientation of a body in rigid body dynamics is that of angular momentum. That is the role that momentum plays in linear motion is played by angular momentum, and let me denote it by a vector L in describing rigid body dynamics. Angular momentum is a general concept, a general quantity that could be defined for any motion, and but it is particularly useful in describing rigid body dynamics. So, in the next few minutes or maybe the rest of the lecture, we are going to spend time on understanding the angular momentum. To develop the feeling for angular momentum, we are first going to start with definition of angular momentum and then going to describe it for a single particle. So, given a single particle moving in coordinate x, y and z with origin at O, suppose there is a particle moving like this with velocity v, its mass is m, then the angular momentum with respect to O, and I emphasize with respect to O because angular momentum happens to be an origin dependent quantity, is given as mass r cross v, where r is the distance displacement of the particle at any given time. This is the definition of angular momentum for a single particle. How about the dynamics that I was talking about? The change in angular momentum with respect to time, analogous to what we learn in single particle dynamics as change of the momentum with respect to time. Here we discuss change of angular momentum with respect to time is going to be equal to the derivative m r cross v. I am now going to use the chain rule for differentiation. For those of you who feel little uncomfortable, I will leave it as an exercise that you take the components of this cross product vector and do it in terms of component, but I am going to write it directly as m dr dt, that is I take the derivative of r with respect to time cross v plus the second term, because I am using the chain rule, m r cross dv dt. As I said earlier, if you are not comfortable with using the vector quantities directly, take the component of r cross v, maybe take the x component, which would be equal to y v z minus z v y. Take the derivative and see that finally this emerges. So, derivative of r cross v is going to be dr dt cross v plus r cross dv dt, m is common. So, what we have obtained is d L with respect to O dt, where let me just remind you that I have an origin O, x, y, z, particle is moving like this with momentum p, this is r, is equal to m dr dt cross v plus m r cross dv dt. But we know that dr dt is nothing but the velocity itself, and velocity cross velocity is going to give you 0. And therefore, what you are left with is this quantity. In this, dv dt, the derivative of velocity with respect to time is the acceleration. So, I have d LO dt is equal to m r cross the acceleration. M times the acceleration is the force, and therefore, this is equal to r cross f. And we define this quantity to be the torque, and I am going to denote it with this symbol called tau. So, what we learn, and I have derived for you, is that given a particle moving, the change is in its angular momentum, and I always denote with this O, emphasizing the fact that angular momentum is a quantity that depends on the origin, is equal to r cross f, or the torque about O. Notice, while deriving this, I use the fact that F equals ma, that is force equals mass times acceleration, or the second law. Except that now, instead of talking about change in momentum, I am talking about change in angular momentum. Are the two equivalent? So, question we now have is, question is dl dt equals tau equivalent to F equals ma or dp dt. I am doing all this exercise to make you familiar with angular momentum and related mathematics. Let us understand this by considering an example. I will consider the example of conical pendulum, and with that I will show you a couple of things. First, I will show you that the angular momentum indeed is origin dependent, and number 2, these two are indeed equivalent. So, let us do that. Let us take the example of conical pendulum. This is a nice example to illustrate the angular momentum concept and its derivative. A conical pendulum is nothing but a regular pendulum with a rod, rigid massless rod of length L, pivoted at a point here, but instead of moving in a plane, the bob goes in a circle. It is going around in a circle, and this rod makes, say, the angle theta with the vertical. Let me call this point pivot point O, and let this point where this vertical line meets the plane in which the circle is made, let me call this A. Because of the symmetry of the problem, I am going to use cylindrical coordinates that we learned in our second or first lecture to describe the motion of this bob of mass m. It is moving around in a circle. Let this be the origin to start with O. So, first case I take O as origin. In that case, the r vector for the ball is going to be given as L sin theta, this is L sin theta times r. Remember, r unit vector is the radial unit vector in cylindrical polar coordinates, minus L cosine of theta z. Let me also say that this bob is moving with velocity v in the circle. V is always in phi direction. So, velocity v is equal to the magnitude v times unit vector phi. Those of you who have forgotten, let me remind you, for a given origin, the distance in the plane of x and y, the distance is given as r, then this vector is r unit vector, vector perpendicular to this is the phi vector, and vector z is your z vector. So, in xy plane I am using planar polar coordinates, and z unit vector is z unit vector. So, these are given as r and v, and now let us calculate the angular momentum for the conical pendulum. Let me again remind you, this is my conical pendulum. The bob is moving around in a circle with velocity v, is going in this direction. This is origin O, and we have written r is equal to L sin theta r minus L cosine of theta z. V vector is v phi. This is the bob. This is where point A is, and therefore, the angular momentum L about O is going to be m L sin theta r minus L cosine theta z cross v phi. R cross phi is z. So, this comes out to be m v L sin theta z, and z cross phi is going to be minus r. You can check that. So, this is going to be plus m v L cosine theta r unit vector. Therefore, at any given point, let me make it again, at any given point, say here, the angular momentum has a component in the z direction, m v L sin theta, and in the r direction, m v L cosine theta, and therefore, you can see that the angular momentum is going to be something like this, with this angle being theta. This magnitude is m v L, and this angle is 90 degrees. When you work it out, you will see, after all, this is r cross v, so it has to be perpendicular to r, and then from these components you see this is the angular momentum. So, what we have learned by calculating angular momentum about this point O for this bob is that it is perpendicular to this, and its magnitude is m v L. This component has in this direction and a component in this direction. As the bob moves around, the r unit vector changes, and therefore, this component changes direction, whereas the vertical component remains constant. So, let us understand the horizontal component, which is m v L cosine of theta, keeps rotating, and the vertical component remains constant. You can already sense what dl by dt is going to be. So, dl by dt, L about O, is going to be d over dt of m v L sin theta z plus m v L cosine of theta r is derivative. In this, m v L theta z all are constant. So, this derivative is 0. In this, m v L theta are constant, but r unit vector keeps on changing. And if you recall from first or second lecture, dr over dt is nothing but omega in phi direction, and therefore, I get dl o dt as m v L cosine theta omega, and we will see what omega is in phi direction. This you could have also checked, because this vector is rotating in this direction with angular frequency omega. Therefore, the change has to be m v L cosine theta times omega, right. I mean, this is when it moves here in omega times t time, this change is roughly m v L cosine theta omega t. You divide by time and you get this answer. So, what we learned from this is, if I take this conical pendulum, which is moving like this, dLO dt is equal to m v L cosine theta. Omega is going to be velocity divided by this by radius. So, velocity divided by L sine theta in phi direction, which is m v square cotangent theta in phi direction. Is that equal to tau? Let us do that. If I calculate the torque about this point, again r is nothing but L sine theta r minus L cosine theta z cross the force. One force is mg and the other force is tension T. Tension T, you can see, is parallel to r. It does not contribute to the torque, but nonetheless let us write this. Tension T has a component, since this angle is theta, is going to have a component T cosine of theta in z direction minus T sine theta in r direction, and I have a minus mg in z direction. You calculate all this and you are going to get r cross z. R cross z gives you minus phi, and therefore, you get mg L sine theta in phi direction, and everything else drops out. You can work this out very easily. So, what we learn now is that this quantity, which is dl dt, and this quantity, which is torque about O, must be the same, and therefore, we get m v square cotangent theta is equal to m g L sine of theta, both were in phi direction. M drops out, and therefore, we get v square cotangent theta equals g L sine of theta. This is what we get. The maximum I can get from this is theta as a function of v and gl. So, again I raise the question, is dLO dt equivalent to f equals dp dt? The answer seems to be no, because only thing I am getting from here is the angle theta, whereas f equals dp dt also gives me the tension. Let us see that, and then we will understand it better. So, when this bob is moving in a circle like this is the tension T in the rod, this is mg. This component of T provides a centripetal acceleration, and therefore, T sine theta must be equal to m v square over the radius of the circle, which is L sine theta, and T cosine of theta must be equal to mg. We get two equations here, and therefore, we can solve them to get two quantities, that is theta and tension both, whereas when we are applying dl by dt equals tau, we are getting only one equation. The reason is that when you take cross products, some components drop out. So, what is the way out? But let us first solve this. So, from here I get T equals mg over cosine of theta, and when we substitute it in this equation, we get mg over cosine of theta equals m v square over L sine theta, and there was a sine theta here also. M drops out, and therefore, we get g L sine theta equals v square cotangent theta, an equation that we had obtained earlier. However, these equations also gave me T. To find T using the torque equation, what I have to do? I have to find another equation, and that equation comes if I take torque about this point. Earlier we took torque about this point, angular momentum about that point. Now we are going to do it about point A. So, let us again see, if I take A as origin, then r with respect to A is going to be equal to L sin theta, that is this distance L sin theta in the r direction, and velocity is nothing but v phi, and therefore, angular momentum about A is going to be m v L sin theta r cross phi is z. You see, when I take angular momentum about point A, only the vertical component remains, the horizontal component has vanished, and therefore, when I take d L A over d t, everything on the right hand side is constant, and therefore, this comes out to be 0. If that is the case, torque about point A must also be 0, and let us figure that out now. So, what we have learned, if I take L about point A, I get d L A d t is equal to 0, and this also must be equal to torque about point A. This is the tension. Let us calculate torque about point A, and I am using a strictly mathematical definition, r cross F. R is nothing but L sin theta in r direction cross F is nothing but t cosine of theta in z direction minus t sin theta in r direction minus mg in z direction. R cross r is 0, and therefore, when I take torque about A, I get t r cross z is minus phi, t cosine of theta minus mg times L sin theta in minus phi direction, and this must be 0, because dLA dt is 0, and this gives me t cosine theta minus mg is equal to 0, or t equals mg over cosine of theta, which is the same result as I obtained from the Newton's second law, direct application, F equals dP dt. So, what we conclude is that dL dt is equal to tau is absolutely equivalent to dP dt equals F. The only subtlety is that in applying this, I may have to take torque and angular momentum about two different points.